Welcome to my video course on railway safety and systems engineering. Today, we're diving straight into how massive, complex networks actually function in the real world. It's incredibly easy in engineering to get tunnel vision, to just hyper-focus on the specific piece of equipment right in front of you. But in high-stakes environments, losing sight of the bigger picture isn't just a mistake, it's downright dangerous. So let's explore the core concepts that keep massive, multidisciplinary projects safe, integrated, and on track.
We're taking a macro to micro approach for this one. We'll quickly define a system, shift into the systems thinking mindset, break down the core engineering principles, and then see how it all integrates into a functioning railway.
All right, Section 1, defining a system. Before we can engineer anything, we need to establish exactly what we're talking about. The absolute defining factor here is intention. A system is a set of elements, subsystems, or assemblies brought together to achieve a specified purpose. It is never accidental. Every single piece is intentionally integrated to hit an overarching goal. Basically, if a piece of hardware or a line of code doesn't actively contribute to that specific purpose, it simply doesn't belong. Fundamentally, every system is a delicate balancing act of three things: people, products, and processes. We engineers usually fall into the trap of thinking a system is all about the hardware and software, the products. But without the people to operate them and strict processes governing how they're used, the whole thing completely collapses. Tweak just one staff role or update a single maintenance manual, and you've instantly altered the risk profile for the entire network.
Now, here's a really vital distinction. An individual component, like a single electrical relay, is highly predictable. We design it so that if it fails safely. But a complex system, that's an entirely different beast. Its behavior is driven by complex, overlapping interactions between multiple parts and the outside world. Intuition won't save you here. The dynamic relationships between the parts completely dictate the final outcome. And that leads us to one of my favorite concepts, emergent properties. These are qualities that literally do not exist in any individual element on its own. Think about it. You can't hold a single piece of copper wire or a microchip and measure overall journey time. Total availability, efficiency, and system-wide safety only emerge when everything is properly integrated together as a whole. You absolutely cannot just bolt safety on at the end of a project.
Moving to Section 2, systems thinking. To actually capture those emergent properties, we have to adopt an entirely different mindset. You can think of systems thinking as a mindset specifically designed for managing uncertainty. It forces us to look at a problem within its true, messy, environmental, and operational context, rather than in some perfect theoretical vacuum. It's all about recognizing what you know, being aggressively honest about what you don't know, and fully understanding that your specific piece of the puzzle is never operating in isolation. To pull this off, you need a very broad set of skills. You have to seamlessly integrate people with technology, all while operating under brutal physical constraints, whether that's a confined physical space, extreme weather, or heavy electromagnetic interference. But above all, you can't just be an expert in your own hardware. You have to anticipate exactly how your gear will behave when it interacts with a completely different discipline's equipment. All right, Section 3, systems engineering principles. We have the mindset down. Now let's apply the actual framework. The entire goal of systems engineering is to remove uncertainties. By creating a highly reliable, shared concept of the system among all the stakeholders, we make sure a massive project can be built with virtually zero risk of rework. It brings order to the chaos, providing us with a proven framework to organize immense amounts of multidisciplinary work. The process itself is incredibly structured and logical. It kicks off by clearly identifying and quantifying exactly what we are trying to achieve. We don't just jump at the first idea that sounds good. We develop alternative design concepts, select the absolute best one based on hard data, implement it, and then rigorously verify that it actually meets those day-one goals. And remember, this isn't just for the design phase. It applies across the entire system lifecycle. It moves from those initial day-one concepts, straight through manufacturing and installation, but it explicitly includes the decades of operation and ongoing maintenance, right down to eventual decommissioning. Good systems engineering cares just as much about how a network is disposed of 20 years from now as it does about how it's built today. Now, your secret weapon early in this lifecycle is the system architecture. A brilliant architecture strategically places boundaries where the interactions between elements are the weakest. By smartly aligning both the technical and organizational interfaces, it separates concerns and makes integration, testing, and future maintenance infinitely easier down the line. Driving all of that architecture is the system requirement specification. Interestingly enough, good requirements shouldn't actually describe specific disciplines or individual parts. They need to be crystal clear, measurable, and strictly focused on system-wide performance outputs, like demanding a network capacity of 24 trains per hour. Achieving that output requires multidisciplinary delivery, backed up by absolute top-to-bottom traceability. Which brings us to our final stop, Section 4, integrating the railway. Let's bring all this theory into the real world. There is a massive trap in complex projects, and it's called subsystem optimization. That's when one discipline makes their specific part highly efficient in total isolation. But true success requires system integration. You can have the most optimized software ever coded, but if it doesn't coordinate flawlessly with the physical track hardware, the entire system fails. We always have to optimize for the whole, never just the parts. In a railway context, successful integration yields some incredible emergent properties. We're talking about overarching safety and rock-solid fault tolerance. We are looking for reduced overall journey times, near-perfect system availability, and high maintainability so things are actually easy to fix. We even have to factor in electromagnetic compatibility to ensure all these diverse electronics play nice together. That is how you measure genuine system-wide success. But as we integrate all this incredible tech, I want you to look back at our very first definition. Engineering loves to focus purely on making hardware fail-safe and software robust. But what about the operators? Human error is almost always a symptom of poor system design. I mean, how reasonable is it to expect operators to just memorize a massive manual or operate flawlessly without intuitive design? If you ignore the people, your system will eventually fail its safety goals. Understanding exactly how people, products, and processes interact to create those critical emergent properties is the absolute heart of systems engineering. Master this, and you can navigate the massive complexities of modern infrastructure safely and reliably. So as you look at your next project, ask yourself, what is the true specified purpose, and is your piece actually serving the whole? That wraps up our introduction. Thanks. We can see you next video.